Okay, thank you. Can you see our screen? Can you see our presentation? Okay, so this presentation.
Yes, we can see the presentation.
Okay, fine. So, hello everyone. This presentation concerns the analysis of micropollutant in wastewater-related matrices and their application. It will be given by Julien, you already heard this morning, and myself, Régis Moilleron. The main objective of this presentation is to explain why it is important to have knowledge about the level of micropollutant in the urban environment and how is it possible to analyze them. So first of all, some background about micropollutant in urban environment. Micropollutant can be found in a urban environment from a wide range of sources. They come from different families of chemical products. They come also from families with different properties, physical chemical properties. And as you can see on this slide, we can find micropollutant in personal care products, household chemicals, pharmaceuticals, chemicals in daily life articles, in pesticides, but also in the composition of industrial chemicals products. And this contaminant end up in wastewater. And it is important to note that when we are speaking about wastewater, we speak about industrial wastewater, but also domestic wastewater. And concerning domestic wastewater, there is two types of domestic wastewater, the grey water and the black water, which is the water generated by flushing toilets, which contain urine and fecal matter. If we are living in urban environment, the sewer can be either combined or separate. In the case of combined sewer, during a rainstorm, runoff is mixed with wastewater, and this mixing ends up at the wastewater treatment plant, and there could be some discharge to the surface water. But if the quantity of water of the sewer water is exceeded, there is direct discharge without treatment, which is called the combined sewer outlet. So therefore, there is some discharge of partially treated wastewater effluent to receiving water, and these discharges contribute significantly to water pollution from micropollutant. As a consequence, the surface water quality is degraded. There is a need to increase the level of water treatment to produce drinking water, because we want to remove those micropollutants from drinking water. And the price of the water quality is increasing. As a consequence, there is a need to increase our knowledge about the quality of wastewater treatment effluent. The idea is to limit as much as possible the direct release of contaminant. This is what we call the Swiss approach. The idea is to upgrade treatment in wastewater treatment plant to reach a removal of at least 80% for 6 compounds out of 12 micropollutants. This is an ordinance from 2016. Or there is another approach possible, which is the knowledge on level about micropollutant concentration in wastewater. In this case, we want to identify source control of the concentration of micropollutant in effluent, but also in influent of wastewater treatment plant. This is what we call the French approach by opposition to the Swiss approach. In this case, this is a diagnostic amont in French, or the upstream diagnosis, in which 96 micropollutants are monitored. Why is it so important to measure micropollutant in wastewater? It's because wastewater are a proxy to better understand changes in urban consumption practices. This is what we call the water-based epidemiology. This was a concept launched by Choi et al. In 2018. Wastewater characterization is very helpful to determine consumption of or exposure to chemical or pathogens in the population. I give you here some examples. This is what we did during the COVID crisis by measuring SARS-CoV-2 in wastewater. It has been done in Australia, Japan, North America, and France, for example. But it could be helpful to measure legal or illegal drugs in wastewater, pharmaceuticals, personal care products, such as parabens in cosmetics. But it could be also helpful to have an idea about the chemicals used in the formulation of industrial product. Here is a view of what wastewater-based epidemiology could be used, because you can have some information about the use, as I said, of illicit drugs or licit drugs, but also about industrial chemical markers about the population, but also some aspect on the social issues. So water-based epidemiology is very important in order to get a better knowledge about wastewater contamination by micropollutant. But if we want to get some better idea of what is the contamination or the dynamic of micropollutant in cities, we need to create what we call an observatory. And this observatory could be very useful. It combines two things: the observation of changes in consumption through surveys. It also helps to monitor the wastewater quality based on properly chosen indicators. And the idea of combining the two approaches, consumption changes and wastewater quality monitoring, is to identify indicators that could help to launch a potential alert. In this case, this alert must be accompanied by a risk assessment to determine whether or not solutions need to be put in place. If so, if some solutions are needed, the public authorities, here in red, must be alerted to define the best solution. And if there is no solution, we maintain the alert, the observation, until the next alert. The whole procedure is then repeated. Such a city observatory has been launched in Paris in 2020. And this observatory will last for 10 years. And it is operated by SIAP, which is the Greater Paris Sanitation Authority. In the case of this observatory, we are monitoring two types of matrices on a monthly sampling basis: sludge and raw wastewater. The idea is that for this monitoring, we measure 65 micropollutants coming from pesticides, biocides, pharmaceuticals, flame retardant, trace metals, but we also measured pathogens, 7 of them, and 15 viruses. Combined to this targeting screening, we also perform non-targeting screening by high-resolution mass spectrometry based on gas chromatography and liquid chromatography. Just to show you the type of results we get so far, the monitoring started in 2025, so we already analyzed 25 samples. Some pollutants were never detected, 11 of them, such as sucralose, heptachlor, and estron. Some others were detected at a rate between 20 and 20% of occurrence, 10 of them, isoproteron, foreign nonylphenol, octylphenols. Some other pollutants were observed at a rate comprises between 20 and 80% for 15 of them. A pesticide, the urine, mercury, a flame retardant, pH, and 17-beta estradiol. And some pollutants were detected at rate higher than 80% for 27 of them, cypermethrin, zinc, copper, etc. Concerning viruses, 7 out of 15 were detected more than once, and for pathogens, all were detected at level comprising between 10 to the 4 up to 10 to 10th colony forming units for 100 mils. So this is what we get as a result for the targeted observation. Now, Julien will speak about the non-targeted screening.
Yes, so in addition to target screening, which targets families of compounds that are known, the goal of non-target screening is to analyze most of the compounds that can be detected by our instruments, by high-resolution mass spectrometry. And this is quite important because there is an increasing number of substances on the market and registered. So we cannot follow by target screening all the molecules that are created every year and that will be created in the future. So that's why non-target screening can be complementary to analyze such new molecules that could emerge as new compounds in the wastewater. And also we could follow temporal trends to check if there is an evolution of some forbidden molecules, for example, decreasing with time, or some new molecules increasing with new uses. So this also a few results that we obtained in the first years of the observatory. From the large number of signals we can obtain from non-target screening, all the signals detected by the machine, we can perform some principal component analysis, and this is just an example of results where we analyzed the different months of 2021, and we could separate clearly all the different months based on the molecules that are detected. So that's promising for the future. So we will be able to detect molecules specifically at each month or each period of the year specifically. So that's interesting, and we hope to obtain such results in the future for each year. So a few details now on the methods we used for non-target analysis. And this is our instrument that we have in Créteil. It's liquid chromatography. It's typical liquid chromatography with a C18 column. And we analyze it in electrospray mode. And the detection is with quadruple and time of flight analyzer. But the specificity of this instrument is that we also have ion mobility spectrometry, which is an additional separation of molecules of ions based on their size and shape. So it's another layer of separation to identify more easily the molecules. On the sample preparation steps, we have developed a method a few years ago now, based on solid phase extraction on homemade multiphases cartridges. You see these cartridges here. They contain 4 phases, 4 adsorption phases, which are HLB, NB+, XAW, XCW. And this has been developed in Switzerland to collect many molecules of various properties. And it's more comprehensive than what we can just obtain with typical solid phase extraction with just one phase. So typically we will analyze 500 milliliter to 1 liter of aqueous sample of water, but it can also be urine, for example, and then it's filtered. It's filtrated on the cartridges for extraction, and then it's evaporated. We pass the extract to solvent, and then it's analyzed in our instrument. Recently, we had a PhD student, Nina Wynn, who performed some experiments on different types of cartridges to know if the method we had with the 4 phases was really interesting specifically for wastewater effluents that were ozonated. So for the extraction of ozone-specific compounds produced during ozonation. And she found out that with the specific cartridge, this one, DPA6S, we could have a more important proportion in red here of products formed after ozonation. So we imagine that we could replace some of the phase that we used before by this new phase to recover more of these byproducts that are formed during ozonation. So that's promising for oxidation processes like I shown this morning. We also developed some methods for solid samples, for sludge and for soils. And this is based on the Quechers method with the solvents and the salts, and then agitation and filtration. And then we add another step of extraction with this 4 phases cartridge, with this cartridge, and then we evaporate and we obtain the extract and we analyze it in the same way than the water samples. So we've been we have applied this method to sludge from wastewater treatment plants in collaboration with SIAP, who started this wastewater observatory in Paris, and we analyzed this sludge which has been obtained after dehydration and thermal digestion. And we've shown here, it's not really clear on this graph, but we could be able to show that the Quechers method with the additional SPE extraction step was able to recover a lot more of compounds than what we obtained just with a simple Quechers method. In parallel, we also analyzed these samples for pharmaceuticals with the targeted analysis with typical quantitation with UPLC MSMS. So that's a few results we obtained. We also talked about urine separation. We showed you before this project that we have on urine separation and spreading of urine on soils for agriculture. It's urine collected in a building, and we want to determine the pharmaceuticals present in urine and also their accumulation in soils. This is a collaboration with another lab. So we are able to analyze them in our lab, but we also analyzed the molecules, different molecules in with this collaboration. So they analyzed around 40 pharmaceuticals, some antimicrobials, and caffeine. And they mostly use a similar method than us with a Quechers extraction for soil samples, for solid samples, but they don't use an SPE like us with cartridges. They use online SPE, so it's just some cartridge in front of the instrument. And for liquid samples, they don't do any previous extraction. They just analyze directly with the online SPE injection, and they are able to reach interesting levels around the nanogram per liter levels. In parallel, we have also for this project with the non-target screening with 2 main approaches. With this type of methods and instruments, we can choose if we want to look for compounds that we already know, not quantitation of them, but in a suspect screening mode. We have a database of around 350 molecules that we are able to detect with this instrument. And it's mostly also pharmaceuticals, but also metabolites and degradation products that we obtain in the lab. So each time we analyzed on the instrument, we can check if one of these molecules in the database is present or not in the sample. And we also have the fully non-target approach, where we can try to get discriminating markers with some statistical approaches like PCA I showed before. And then we can try to identify new compounds that were not in any of our database, but we can try with their potential structure to identify them in the sample. So it's a bit some words on this method, because it's very data intensive, and it's large data. It's difficult to analyze. So we had to develop homemade statistical methods and applications. So we with some PhD students, we are developing interfaces and statistical methods based on R language or Python language for fast visualization and advanced statistics. And it's mandatory to be able to analyze this data quickly and easily, or else it's very difficult. So a few applications of these methods. This was a project that we had in our lab. And thanks to these statistical methods and non-target analysis, we were able to detect in road runoff samples, so some water that was collected near a road with high traffic in near Paris. We were able to identify some very intense molecules, and especially this molecule here. It's diphenylguanidine, which is an additive used for the synthesis of tires. And this molecule is released by the tires when it's raining, and it's going to the water and to the soil. And we showed also with some colleagues that it can be associated with some ecotoxicological effects on zebrafish. So it's important to analyze this and to show it's present in the samples. In the same project, we tried to analyze, to detect in suspect screening mode these molecules, but also other additives that can be released from tires and from cars, such as benzotriazole, and we were able to detect them in the samples and in the soils. In our lab at LESU, we also analyze a lot of molecules from various sources, mostly from industrial sources. It's been like almost 20 years that we analyze all these families of compounds. We target industrial surfactants like alkylphenols, conservative like parabens, industrial plasticizers like phthalates, and more recently we have a lot of projects going on biocides that are used not only as pesticides but also as disinfectants in products that are used in the households, for example, by people directly at home. And so a few examples on these compounds that can be released by cars. Some of them are also released by cars, but they are released and emitted in wastewater. And we analyzed some of them in the road runoff samples. We also checked these industrial and plasticizers compounds in wastewater treatment plants, and we checked how they are removed or not by the treatment steps. So here, for example, you can see DEP and DEHP, which are phthalates. They are quite eliminated in the biological treatment, but other compounds like alkylphenols, nonylphenols here, NP, are not well removed, and so they are in high concentrations, around the microgram per liter in the wastewater effluent. So as I said, we are recently we focus on biocides, and some of them are emitted from building materials. And so this is different types of biocides, different families that can be emitted by building materials or can be found in households. Some of them were used in the past as pesticides. You can see here diuron. It has been forbidden for use as pesticides, but it still can be used for building materials, for example. So it's still present in the urban waters, in wastewater. And so they have some ecotoxicity, and so it's important to target them. So we analyze them in the lab with two approaches, with the dissolved fraction and the particulate fraction. So we filter the samples and we separate both fractions. And the dissolved fractions is analyzed after a solid phase extraction, like I shown before, and the particulate phase is analyzed with microwave extraction. And all of this is quantified by liquid chromatography and mass spectrometry. So a few results on these biocides. We had a PhD student working on this who found the different trends and different concentration of all of these biocides between wastewater in the wastewater treatment plant and stormwater from combined sewers overflows. And she found interesting results. Some of the molecules were much more concentrated in the stormwater, in runoff water, than wastewater. It indicates that they are more produced from buildings, from runoff on the buildings. And some other molecules are much more concentrated in wastewater. So it means that they are more used in household, in domestic uses, and released in the end in wastewater. And some other molecules have equal concentration, so they are both used outside and inside buildings, and they can be found both in stormwater and in wastewater. So that's all for our overview on what we analyze in our lab from both target screening of families of compounds that we target in the lab, and non-target screening with more unknown compounds and try to identify emerging compounds. Thank you for your attention.